Okay, welcome to our new unit on weather. So today we're going to be talking about air pressure, which is our first lesson. It's pretty short. It's an introduction to a lot of things we're going to have to know. So the way this unit works on weather is there's going to be a lot of small lessons that build up, and as we go through each lesson, they're going to build on one another. So we're going to talk about air pressure today, and then tomorrow or the next day, we're going to talk about what air pressure can do. And then from there, we'll talk about what kind of weather that is associated with. So all of this is going to build up over time. It's just so you're aware of that. So today for air pressure, we want to convert between inches of mercury. Hg, okay, is mercury, and millibars is another unit of measurement for air pressure. And then we want to describe how temperature, water vapor content, and altitude can affect air pressure. So there's going to be 3 things that we're talking about today, and we need to be able to explain how those 3 things are going to affect our air pressure. So our success criteria, you can define air pressure. You can use a reference table, I believe page 13, to convert pressure between inches of mercury and millibars. And we're going to describe how those 3 factors, how pressure changes with water vapor, altitude, and temperature. So you're definitely going to need your reference table for this lesson and any other assignments that go along with this, so make sure you have it. The first thing we want to know is what is pressure. Another word for air pressure is barometric pressure, so you may hear that sometimes. So if you see this word barometric, okay, just know that this is air pressure. Air pressure is the weight of the air above us pushing down. So if we think about the atmosphere, all of the layers going miles and miles above our heads, there's all these molecules, nitrogen and oxygen, pushing down on us. So it's the weight of all of that pressing down on us at the surface. We measure it using something called a barometer. So remember in the last slide, I said it was barometric pressure. So we use a barometer to measure our air pressure. And we measure it in either inches of mercury, so Hg is mercury, or in millibars. And both of these are going to be given to you on your reference table, and sometimes you're going to have to convert between them. You have to know which is which. Here's an example of a barometer. So this one is measuring in mainly inches of mercury. These big numbers here is 28, 29, 30. Notice that there's weather also associated with it. So we're going to talk more in the next lesson about how the weather is impacted by air pressure. We have very dry here with a higher air pressure of 31, stormy with a lower air pressure of 28. Here's another example. This is a barometer that's using mercury. So the air is pushing down, it's forcing the mercury up the tube, kind of like a thermometer. When you take your temperature, the alcohol or the mercury moves up through the tube to give you a reading. You're not going to have to take measurements, but you are going to have to be able to convert measurements using your reference table. So here's a weather map. This is an old map. This is from March 2015. It's just to show you examples of high and low pressure. Okay, so we're going to do a lot of weather maps. Here's a high pressure here. Notice the H's are blue. The L's for low pressure are red. We're going to talk about what that means later on. And then we also have these frontal boundaries here. So these are color-coded for us, which is great. So blue is typically colder. So here's a cold front here. Here's a warm front here in front of this low pressure. Here's this high pressure. And then here we have what's called a stationary front. We can also have occluded fronts, which are the purple ones. We can't really see them, but just so you're aware, we're going to go through all of this as we go through these lessons. And you can see that as the time goes on, so here's the timestamp, all right, down here. Here's the date, 31st of March, 2015, 1547 GMT. That's a global or Greenwich Mean Time. That's the time it is in London or in Greenwich, England. So we're going to go ahead another hour. And what you notice is that these highs and lows are going to move a little bit across the United States. And something that we want to start looking at is what is the trend, or what direction do we notice weather moving across the United States? not going to give you an answer to that right now, but something to think about. So here we have our chart. This is in our reference table, so this is going to be page 13. Okay. And what we want to be able to do here is we want to be able to look at the chart and convert. So the first thing I want you to notice is here we have labeled 1 atmosphere, our 1013.2 millibars. Okay, this is standard. So we'll say standard. Don't mind me. This is standard pressure at sea level, okay? And it gives it to us in millibars, and then in atmospheres, 1 atmosphere, and it is not given to us in inches of mercury, but that is on this side. So in order to make that conversion, we have to look at how these numbers are increasing, right? So if I'm here, so if I want to read this chart, like I want to know what is 1 atmosphere in inches of mercury, or 1013.2 millibars in inches of mercury. I know I have 1013.2 here. Here I have 29.9. Here I have 30. So in between here, I need to figure out what each of these teeny tiny little lines is going up by. So notice in between 29 and 30, okay, I'm only going up by 0.1. So that means that each of these lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, right, each of these lines is going up by 0.01. All right, so here I have 29.90, 29.91, 29.92. All right, so standard pressure in inches of mercury is 29.92. And we're going to practice with this a little bit more. So our inches of mercury side, the little lines in between are each going up by 0.01. In millibars, here I have 1032, 1036. This is 4 millibars in between here. And in between each one of these is 1 millibar. So this side's a little bit easier as far as numbers go to look at. Okay, so I did this first one with you. For our air pressure conversions, we said 1013.2 millibars equals how many inches? All right, so we said 1013.2 is 29.9192 inches of mercury, or 1 atmosphere. Okay, this is standard at sea level. And then we have 1022.8 millibars. Okay, so here is 22.8, so almost 1023. These are done to make it your life a little easy. If I go across here, it looks like it's 30.2 inches of mercury, or 30.20 inches of mercury. All right, so then I have 1005.0, there should be a 0.0 here, 1004, 1005, all right, and then if I go across, it's right here, 29.65, 66, 67, 68. Looks like it should be right around 29.68 inches. If you get 6.9, that's okay. So why don't you pause the video and try the next one on your own. All right, so if we're looking at 985, hopefully you did this one on your own. Here's 984, 985, 29.9, okay. Sorry, 29 point, this is 29.00, so 0.05, 0.09 inches should be the answer. Again, if you're a little bit off, if you get 29.08, that's okay. It's definitely not going to be correct if you go up to 29.1, because it is not all the way up there. Okay, the next thing we're going to do is we're going to go backwards. So we're going to go from inches of mercury to millibars. I find this to be a little bit easier sometimes. So if I have 30.53 millibars, 30 0.5, 1, 2, 3. I have 1,032, 1,033, 1,034 millibars. So that one's pretty easy. All right, 29.81, 29.8, 29.81. If I go across, I have 1,008, 1,009, 1,009.5, somewhere in that range. Okay, it's definitely not 1,000.9, it's definitely not 1,010. It's somewhere in the middle. You're going to have to estimate that decimal. So we have to practice that skill of estimating decimals. All right, the next two, I want you to take a minute and try on your own, and then come back and see if you get the right answer. Okay, so if I have 29.12, 29.12, I go across, looks like it's going to be 984, 985, 986. And 28.67, 28.65, 6667, 971. Okay, so hopefully you feel pretty confident converting those air pressures. This is as complicated as it's going to get. So if you can do this, then you're in good shape as far as this learning target goes. So here we go. We completed this learning target. All right. So now we're going to talk about isobars, which we talked about isobars way at the beginning of the year. Okay. These are lines on a weather map that connect areas of equal pressure. So we're looking at a weather map. A lot of what we see is temperature and pressure. So we're looking for areas of similar temperatures and areas of similar pressures. So isobars that are close together, so show us rapidly changing pressure. And this is something we're going to be talking about, and we're going to have to look at weather maps and be able to kind of decipher them a little bit. So we're going to talk about what it means when I have these lines, so these red lines. This is a National Weather Service map. So this is not the map you get from the Weather Channel, but I can provide you a link so that you can find these maps if you want. Here I have a low pressure over here. Notice the numbers are written here, so 980. This is fairly low pressure. It's going out as I extend outward from that low pressure. And in this area here, it's fairly close together, these lines. We're going to talk about what that means. But when you have a rapidly changing pressure, it means it's windy. So on a day that's very windy, like the last few days have been, let's see, like this is from Friday, April 3rd, 4:32 global time. So that's in London time. It was pretty windy Friday. So this kind of shows us, oh yeah, here it is. These lines are close together. That's what that means. All right, so now we're going to move on and we're going to talk about these three factors that affect air pressure. First one is temperature. So as temperature increases, air is expanding. So if we think about the molecules in the air, right, the air expands when it gets warmer, and we talk about when we talk about molecules, we talk about phases of matter. We talk about how molecules move or vibrate in different phases and how adding temperature is going to increase their rate of motion. So as air temperature increases, the air is expanding, and density and pressure are going to decrease. So those atoms here, these blue ones, they're going to be forced farther apart, because that air is that temperature change is creating more vibration in the molecules. Temperature is just a measurement of average kinetic energy. It actually doesn't mean the same thing as heat. When we looked at the thermosphere, when we looked at the atmosphere layers, the temperature was very high. But what that doesn't really tell us is how much heat there is, because just because there's a high temperature doesn't mean it would be like hot to the touch. It just means there is a high rate of average kinetic energy. So if you have a very few molecules very far apart and they're moving very quickly, the temperature will be high, even though it might not feel that way. So as temperature decreases, air contracts. Okay, so here we have hot air. If we decrease it, those molecules are going to contract. They're going to come closer together. Density is going to increase because you're going to have more things closer together, and pressure is also going to increase. Okay, so temperature and pressure have a direct relationship. or indirect relationship. I'm sorry. Temperature and pressure have an indirect relationship. So if one is increasing, the other is decreasing. The next thing we're going to talk about is water vapor, and we're going to talk a lot about water vapor and water in the air as we move through this unit. So the more water vapor or humidity in the air, the less air density and pressure. This may seem counterintuitive, but this is something we just are going to have to learn, and I'll explain to you why. All right. So we know that oxygen and nitrogen make up the majority of the molecules in the atmosphere, in the troposphere, specifically where we live. Water molecules actually weigh less than oxygen and nitrogen molecules do. So if we look at the atomic masses, right, we look at O2 and N2. I'm going to do it here. Here I have nitrogen. Okay, so air molecules, mostly nitrogen, and nitrogen has a mass of 28. Water molecules, which is H2O, 2 H's is 2, a mass of 2. Oxygen has a mass of 16, so the total mass of a water molecule is 18, and nitrogen has a mass of 14, so the mass of each of these air molecules would be 28. So these weigh more than water, like their atomic mass is more. If you replace a nitrogen with a water molecule, you're actually decreasing the amount of mass here. So if we look at the total mass of the air molecules here, if we have 30 molecules times 28, that gives us a mass of 840. If we have 24, so we replaced some of these nitrogens with water, we get 672, and then 6 of them times 18 is 108. Our total mass here is 780. Our total mass here is 840. Okay, so water weighs less than air. And that means that air pressure is lower when you have more water vapor. Okay, so this is going to be important when we talk about weather events like storms and rain, etc. So whenever it is humid, very humid, or a lot of water in the air, we typically associate that with some kind of rain event, whether it be a hurricane or just a rainstorm, whatever. But those days are always associated with lower pressure than days that are clear and sunny. All right, the third thing we want to talk is about altitude. So remember, altitude is your height above sea level. We talked about that when we talked about the atmosphere. So as the altitude increases, as we go up, right, into the atmosphere, our air density and air pressure decrease. So the reason for this is that there are less molecules or less air above you. We said at the very, very beginning of this lesson, the definition of air pressure was the weight of the air pushing down on you. If you go up into the atmosphere, there's less air above you. So there's less stuff pushing down on you, just like if you go into the ocean. Same idea. Ocean has a lot of pressure, right? So if you go deep into the ocean, you have all the weight of all of the water on top of you. That's why we have to have special submarines in order to go deep underwater and explore. If you are going towards the surface in a submarine, you have less and less water above you, so that pressure is going to decrease. And we can see that here. We have a greater amount of air molecules down here. They're more tightly packed. They're closer together, right? And then as we go up into the air, okay, we have fewer and fewer. They're just more spread out here. Here is a diagram of air pressure measurements on one side, and then we have feet in like this green color, and then meters in white. So here we have Mount Denali in Alaska, which is 20,000 feet. That has a pressure in millibars of about 450. Okay, remember 1032 is average pressure at sea level. Or I'm sorry, not 1032, 1013.2, my bad. 1013.2 is average at sea level. That would be down here. And then as we go up, we have less and less and less air pressure above us. All right, I mean, this is really all we're going to talk about today. So just as our summary goes, so if we have altitude, temperature, or water vapor in the air increase, the air density and pressure will decrease. So all of these are inverse relationships. As one increases, the other is going to decrease. So some questions we're going to just review, okay? So you can pause the video as we go through this. So the first question is, as air gets warmer in the atmosphere, what happens to the air pressure? As air gets warmer, the air pressure decreases. So remember that the molecules are getting farther apart as it gets warmer. Temperature is a measure of average kinetic energy. So as those things are moving apart, air pressure is decreasing. At sea level, the average air pressure in millibars, all right, let's get this right this time, 13.2 millibars. Okay, and that's right in your reference table. You do have to read it. It's also 1 atmosphere. We also said it was 29.2, I think. 29.92 inches of mercury. Here we go. So here's 1 atmosphere, 1012.0, 1013.2, 29.92 inches of mercury. At sea level, the average air pressure in inches of mercury is, okay, so I gave this away already. And as altitude increases, so as we go up, what happens to air pressure? Air pressure is going to decrease. Remember, you'll have less air above you, less things pushing down. As air gets more humid in the atmosphere, the air pressure is going to decrease. And remember, we said that water weighs less, so those H2O molecules have a lower weight than the nitrogen molecules do, or even the oxygen molecules in the atmosphere. So you're going to have lower pressure as you have more humidity in the air. So here's some practice questions we can look at. A barometer, okay, is used to measure pressure. So barometer is used to measure barometric pressure. These are easy questions on an exam where you'd just be asked to identify which instrument is used to measure which variable in weather. As air absorbs moisture, its density does what? So if we increase our moisture or humidity, the density is going to decrease. As your height above the surface of the Earth increases, the atmospheric pressure usually decreases. Atmospheric pressure is often measured in, okay, so these two are temperature. This is density. The answer is 4 millibars. Atmospheric pressure is a result of what property of air? It is weight. It is the weight of the molecules around us. All right, so hopefully we have completed our learning target. If you still are not sure about any of these two things, converting or describing the relationships between temperature, water vapor, and air pressure, go back and look over the video again, or go back and look at your notes. I hope that this is fairly straightforward. I hope that the narration helps you guys understand better what we're learning about. If you have any questions, please don't hesitate to reach out and ask them. So again, here are our success criteria, and hopefully you can do all of these 3 things now. All right, so thank you for watching the presentation, and I hope you guys have a great day.